Thank you guys for coming to this session, which is on our stormwater and community infrastructure master plan. The quick backstory is we got a grant from the state that is covering the lion's share of this plan that we're putting together. It's done in cooperation with our Department of Public Works, particularly our water department, who've been great partners in this. They have, between us, our department, and DPW Water, we have been working for now coming up to almost 2 years of work to put this together. A lot of field work, a lot of work that's been done in the office, in the back end to put this all together. So we had some conversation about what this project is, what it's trying to do, and what the hopeful end results would be as we wrap this up sometime toward the end of this calendar year. So without further introduction, I'd like to introduce our consultants who have been doing the lion's share of this work. They've been great to work with, Weston and Sampson. In particular, I want to introduce Kara Kelleher and Will Blaze, who have been instrumental in putting this together, who are going to walk us through the program, and then there'll be some time to ask questions at the end. So, without further ado, which is my new catchphrase, I don't use it all the time, Kara and Will.
Thank you. Good morning. So Worcester Sewer Operations Department is in charge of the sewer system and the stormwater system. The city has 374 miles of drain, 370 outfalls, and 29,000 catch basins. So the stormwater system is made up of drain manholes, drain pipes, catch basins, and outfalls. That just gives you a little bit, there's a sewer underneath the streets. There's stormwater pipes or drains, sewers, and water. So, and just to give you a introduction into or definitions about the pieces of it. So a drain manhole are structures that allow access to the drainage system for inspection and cleaning. They're usually at approximately no more than 300 feet apart just for cleaning. They also are located in intersections where you might have drains coming in at different directions, not just flowing straight through. And then that's just a cross section of a typical manhole. And if that's looking down into one, and you can see that there's a drain pipe coming in from like 1 o'clock. And then pipe invert and slope, the way that a pipe conveys stormwater, it's usually by gravity flow. So there has to be a pitch in the pipe, similar to in your house when there's a slope, so the solids and water just flow without needing any mechanical assistance. And the slope is, so an invert is the elevation of the bottom of the interior of the pipe, and the slope is the difference in vertical change and divided by the length. And then catch basins are structures with grates, usually on the edge of the road or curb. And you can see that occasionally in this, they get filled with trash. So the city has a program where DPW has a program where they clean them out regularly. And there is a pipe, you can see that pipe that's curved. That's in there to prevent the trash from going actually into the sewer system. So it sort of keeps it in the catch basin, which is easier to take it out. Outfalls are in the drainage system. So it's where the stormwater exits the pipes. So it could go to a drainage swale, a wetland, or water body like Quincy, the lake, or the rivers. And then a culvert is tunnel-like structure that crosses under roads, rare bridges, or railroads, and then that just carries like an open channel, so a stream under a road. And Worcester DPW has existing programs to address both water quality and capacity issues within the storm system. So the city conducts annual outfall sampling as part of their IDDE program. And the city has also completed numerous analysis, evaluations, designs, and construction improvements of the storm system over the past 10 years. And the drainage master plan, so we started this project in 2022. As John said, the city applied for a grant from the state, and the objective of the drainage master plan is to identify areas where there's flooding in the city. So the green, light green in the center is the combined sewer area in Green Island. So we worked on everything but that. There's another project going on now that is addressing the flooding within the Green Island and combined sewer area. And for our project, we developed a computer model. So it's a hydraulic model for the local drainage pipes. So our model just looks at the pipes and not at the open channels or culverts, like with the open channels. And then future phases of the master plan those will likely be added to a future phase, just to give a more whole approach of the drainage system. And I'm going to pass it on to Will.
Thank you.
Yep.
So the main focus of the main deliverable out of this project was the computer model and the end results of the model. So a little background in hydraulic model. Hydrologic means analysis of the impacts of rainwater landing on the land surface and determining how much of that is captured and infiltrated into the soils or collected within the nature-based designs, and which component of that is runoff that gets collected in the drainage system. So hydrologic gives us the runoff excess that's not taken care of by nature, and that gets brought into the system. Hydraulic model is an evaluation of those pipes and that system based on the slope, sizes, and different configurations and tie-in points, how that system reacts to the runoff hydrographs that are generated in the hydrologic model. Okay, so that's just a little background on what those two things mean. Okay, so the first step is we had to compile. The city has done a lot of work in the past. There's a lot of studies. There's a lot of improvements that have been done. So we compiled the previous drainage studies to get context and, you know, to have correlation between the work that's been done in the past and the work that we continue to do here under this project. Okay, first we needed to identify the limits of the pipe network. Again, it was not including the combined sewer area. So we have a city GIS of the drainage system that identifies the manhole locations, pipe information that's attached to it. And we focused on everything that's owned by the city. There's a lot of drains that are private that are not being analyzed under this effort here. So it's city owned, everything that's tied to their existing GIS system. Okay, so we reviewed the GIS that was provided to us. It's this extensive system, and we wanted to determine, you know, what information is missing in the GIS that is going to be useful for us to populate so we can put it into the model. Okay, we're talking about manhole depths, pipe elevations, pipe sizes, whether it's circular, it's a box culvert, pipe lengths, and then pipe materials of the actual pipes. That information is in the GIS. Some of it's populated, some of it wasn't. So we had to determine a list of information that we needed to collect more information on and fine tune it so we can put it in the model. As far as the process goes, you know, stormwater collection data, we reviewed the city GIS. In the GIS, there's all types of fields in there. Had to determine which ones were useful and populated, which ones needed to be populated more. And so we developed a manhole inspection work plan to establish what areas of the city needed the heaviest inspection and evaluations. And when it was all said and done, we conducted over 4,300 manhole inspections to help populate the GIS, which was not populated at 100%, and then with that information, we can use that to populate the model that we create. The hydrologic process is, develop a hydraulic model by importing the city GIS system. So in this map, you see a figure that shows a certain area of the town, of the city, where, we imported the nodes, which are the blue nodes, basically manholes. And then we have pipes with information that's there. Again, this is just a layout of, this is the system, and this is what we need to develop. Say, this is what we're going to model. This is city-owned drain pipes that are included in the model. And once that has been established, you take that system network that you developed, and then you evaluate subcatchment areas that introduce the flow into the system. Using the subcatchment information that was developed on those maps, we've developed runoff hydrographs for storm events for the 10-year existing and the future projected 2070 10-year flows. So we could get a sense of the 10-year existing tells us, here's the potential problems that you have now. And the 2070 is predicting, where your flows problems could exist in the future. A neighborhood that has flooding problems, doesn't have flooding problems now, could in 2070, based on the rainfall data. So those are the hydrographs that were generated for the hydrologic model and then brought into the hydraulic model. The last component is to develop model validation. We want to be able to go out in the field when it rains, collect data that says, okay, this rain event that we got, this is how the system reacted to it. We document observations that we open in the field when we open manholes, try to get the depth of it, where the flow is, how high it is in the manhole, and things like that. So the citywide master plan had limits of works. Okay, it was basically the 4 watersheds that are contained within the city right now. You have the east watershed shown in orange, west is shown in blue, central north is the brown one to the top, and central south is the green one to the bottom. Those are the 4 areas that are called tributary watersheds within the city. Already been established over the years, not something we created. It's contained within the city GIS currently. And then the green area in the middle is the combined sewer area that was not included under this effort, but is under other work the city is doing. Each watershed was split up into sub areas based on existing drainage components. Okay, so once we have the system figure laid out in the network, manholes, pipes, and outfalls, then we have to figure out how is the flow getting into these pipes and where is it getting into it. So, the watersheds were broken up into sub areas based off of outfall locations and tie-in points to the natural tributary streams. Nodes and subcatchments, how they work together. Nodes are located within the model as usually catch basin tie-in points or points where catch basins tie into manholes. And each sub area was split up into subcatchments based on the entry point into the system. So the number of subcatchments that we developed for this model is well over 7,000 subcatchments, and that was distributed into the model at various points. Throughout the process of the data collection, we had a small task of determining other information as far as collecting system data. So we investigated and inspected 33 outfalls, and that was more of a cursory thing to let the city know where they stand. Again, there's like 330 or 350 outfalls that need to be done over time. This is just a beginning step, and what we're trying to determine there is what conditions are these in? Are the outfalls, collapsed at the end? Are they crushed? Is there a blockage? What's being done there, and why is it potentially causing a problem in the system or in the neighborhood that's flooding? Water can get down to the pipe, but when it gets to the outfall, if there's a blockage or collapse or something like that, the water can't get anywhere. So it has to back up into the neighborhoods. So this is the beginning step of fine-tuning their outfall collection. Again, this is a similar effort, which is culverts that are located throughout the city, which I'm not sure of the number, there's thousands of them. So We started with a small sample of what we're doing here is 41 culverts selected by the town and discussed about potential areas that they were concerned about. And what we did here is we have a zoom camera where you can go and stand at the upstream and downstream end of each one of these. And it's something we can look up into the culvert to see what's going on there. This is a combination of, are there any obstructions, but also are there any structural failures that need to be addressed? So this is the beginning process of collecting that data, not so much part of the model, but the bigger picture effort that's going to continue growing as projects develop. And the hydraulic model metrics. So we have the 4 watersheds I was talking about, east watershed here in orange. You can see it was subdivided into 17 sub areas with over 1,800 subcatchments. So that's smaller areas that take flow, they're bringing it into the system at different points. Okay, 3,100 nodes and 100 outfalls, and 83 miles of drain pipes and over 2,700 acres of land area was calculated. Same for the west. Again, you can see the size of these projects and these watersheds, 2,400 subcatchments, 106 miles of drain pipes, 4,700 acres of land mass that was evaluated. So that east is the one in the orange, west is the one in the blue. And again, central north is the brown one up at the top. A little bit smaller area, 10 sub areas, 1,900 subcatchments, 79 miles, 3,000 acres. And the central south to this is a green one to the bottom, 1,000 subcatchments and 49 miles. So you can see the magnitude of the effort that was done throughout the city through the 4 watersheds. That's kind of the metrics of what was collected and utilized for the model. And this is an example sub-area map. So this is a map that's showing actually the nodes, which are the manholes, which we showed on previous slide, the pipes. But what's added to this is the subcatchments, where these finer subcatchments are calculated, saying subcatchment 25 now goes to manhole 26 on Salem Street. And that's how it gets distributed into the model, and then the flow gets analyzed. So you can see the magnitude of what was done here, 48 sub areas, over 7,300 subcatchments, 370 outfalls, and 315 miles of drain pipe was analyzed under this H&H model project. Once you have the model created, you've collected the hydrologic data, you've collected the system data in the field, you now populated the hydraulic data, which is the system information. Now you have to analyze certain flow scenarios. So the flow scenarios that we've done for this project currently is present day 10-year rainfall event from NOAA, and then the 2070 projected 10-year rainfall event for resiliency evaluations. And that's done citywide through the whole system of the 4 watersheds I was talking about, okay? Once that's done, we evaluated areas of concern, met with the city to establish this is a starting point where things potentially have issues, and we need to focus on where can we remediate problems and how can we focus on making improvements and help the city out with alleviating the flooding. So we sat down with the city. We have a whole metrics of board of how we selected 6 areas through the city, and these 6 areas are in the process of going into detailed evaluation, where we're going to evaluate for different storm events what we can do to help alleviate the flooding, whether it's a combination of gray infrastructure, which it will be, and then nature-based green infrastructure components married together. Again, this is just the beginning process. This is 6 areas out of many, many, many areas that will be done over time as this model and the program develops. And this final map is showing the results of the model. This is a figure showing one of the areas, the similar area that we just showed you. So the manholes that are highlighted in yellow, orange, and so forth, red, those are manholes that flood to the surface and water's leaving the system. Okay. The orange pipes are pipes that are surcharged, meaning the water level is above a full pipe, but it's below the ground. Okay, so it's undersized. It's okay to have a drain undersized as long as it's not, 5 feet surcharge, because then it creates other issues. So this is a result of one of the models for the 10-year, 24-hour present day, said this is the potential problems you could be having in this system currently. So with these results, we look at what nodes are flooding, what nodes are surcharging. We talk with the city, we check back with their inspection records and their complaint files of flooding and all their work orders to see how many events have flooded in this area, because we want correlation between what the model says and what's being observed in the field. So working with that correlation, we come up with 6 areas to get extensive improvements and evaluations down the road, which is part of this project also. So when it's all said and done, the city will have existing and 2070 projected models citywide in all this 4 watersheds, plus 6 areas with detailed analysis and alternatives for improvements going forward. And now Carol will talk about some of the improvements going forward.
So as Will mentioned, we just worked with the city. We just met this week and finalized the selection of the priority area locations. And the criteria for that was observed flooding and documentation in correlation with the model. Then community impacts of flooding. And then we also looked at environmental justice communities within the city of Worcester. And solutions that will be considered will involve both green infrastructure and nature-based solutions, such as bioretentions, basins, swales, permeable pavement, and then gray infrastructure are just, culvert upgrades. So if there's a culvert that's under the street, but it backs up during storm events, making that larger, potentially underground storage in like parking areas or parks, and then drainage pipe upgrades, which would be upsizing the pipe. So if there's a 36-inch pipe or 24-inch pipe in the street, maybe it needs to be 48, or maybe there needs to be a parallel pipe in the street. And this work is ongoing. Just want to give you some examples of green infrastructure and nature-based solutions that will be considered during the assessment of the 6 areas. So constructed wetlands. So if there's a area that, constructed wetland, it's, turning an open space into a wetland, and maybe it was a wetland previously, but now it's just had some fill put in it over the years. And then underground storage. So the lower picture just shows underground storage basins being installed. I think it's going to be a parking lot at a park. That just allows the volume of water to be held during the storm so it doesn't hit the streets. Green roofs. This helps to minimize the runoff of the roofs, and it just also contributes to air quality. And then permeable paving. And I think, and it was on the slide, but I don't think Will mentioned it, but there's a lot of pavement in Worcester. Like if you look out in the parking lot, this is a lot of impervious pavement around the library and near City Hall, although the park behind it is great. Bioretention basins are, usually they're located adjacent to paving, so in parking lots or on edges of the streets. And then tree box filters can be used, again, parking lot medians, sidewalks, or along roads. And then planter boxes and drainage swales. So, and then the next step for the project is we're develop the alternative analysis that's now ongoing. And we'll also identify the, what size the pipe needs to be, what opportunities there are for nature-based solutions, and then also what permits would be required and estimated construction cost. And the project, as John mentioned it earlier, is expected to be completed by the end of the year. And then now just, if you have any questions, we can have time for questions.
I assume the times of travel were rather short, like way under an hour. So when you're talking 10-year storm, you're talking an emergency storm, or maybe I'm wrong. everything. And also, was Holden in any of your critical areas? And if so, I want to talk to you more about that for probably Friday.
We'd have to check it to individual streets again. We can get back to you on that. I don't know off the top of the head if it's one of the 6 areas. There's a couple that I know for sure that are, but I'm not sure if that street is in there.
Yeah, and on the storms, so we did the 10-year 24-hour storm and the 10-year 10-year 24-hour and then 10-year 1 hour.
We looked at them both. There's to establish long duration storms that have higher volume but less intensity versus, shorter duration storms that have high intensity and like a, July thunderstorm or something, which has a different effect.
Right, but I assume your times of travel are almost all.
The TCs are short for the watersheds. Again, these are sub watersheds to the main tributaries. The main tributaries, the Beaver Brooks and all the brooks going through the cities, those would have the large lag times. Right. Good.
So you've just done the current situation. You've just done the current situation for the whole city. You haven't done the future yet.
We have future 2070 projections models run down. Yes.
I guess I was just wondering, do you have a sense when you look at this Worcester system, you probably worked another, are you like, oh, they're in pretty good shape, or like, oh man, they got a lot of, they're going to be people on the hills are in good shape. I mean, I don't know if you have a sense.
I think,
where we're at.
I think the good news is, so areas that flood now, when you apply the future impacts to that, very often it's new areas are not going to be flooding, but areas that flood now are going to be flooding to a higher extent and for longer. Because there's breakout points in the system. So if it breaks out at a low point, the people upstream are not going to have problems because the water's not getting there. So citywide, there are areas that flood in 2070 projection that don't flood now, but a majority of the stuff we've come across it's typical areas that presently flood, but will have higher volumes of flooding in the future. And as far as the rest of the city, I mean, city-wise, you guys are typical as far as where you're headed. The fact that you're highly impervious. Impervious means water that rains, that falls on the land surface, can't get into the soils. It has to be collected somewhere. So highly impervious plus highly sloped streets is what generates a high runoff rate. So there are many communities like that that have, those two factors that drive everything. Well, I'm going to go in order. He was up there.
Can you explain the difference between a fire retention basin and a rain garden?
I'm just going to go back to the picture. We have our resiliency people are going to present later today. So what you said, bioretention basin and what?
And just a rain garden.
So a bioretention basin is for storage. A rain garden is more water quality. So there will be some retention, but it's not as deep. Like there's not as much volume held.
Worcester's an old town, and it was built over decades and decades. Just as a back of the envelope, yes. What design criteria was used to put in the existing storm system, and and what rainfall criteria was used then, or 3 years ago, compared to what's projected for 27?
So most likely the drains that we're looking at right now, the existing drains that are in the city system were probably designed for 10-year, 24-hour storm event. Some of them may be 5. And that was based off a technical paper 40, which is old rainfall that was collected back in the 60s. So back then, it's really about what are the impacts if it floods. So the higher the impact of flooding, the higher the design storm you would use. So if something floods, but it goes down the street and it doesn't affect properties, it's just a small amount of flooding, that's one situation. But if you have a situation where it floods, but then it backs up this culvert and then it closes the road for 3 hours, that would be a 25-year design storm situation. So local drainage is usually 10-year, okay? Now, 10-year today is 4.9, and 10-year 2070 is 6.5
Inches of rain.
inches of rain in that storm event. So the degree of protection you could be getting is for a larger rain event, but it's still going to be classified as a 10-year, 24-hour event because of the weather, resiliency and weather patterns changing and climate change. Rainfall patterns are different. So now NOAA 14 is not using data from 1920 to 1960. They're using data from 1920 to 2000 or 19 around 2000. So they have a bigger data set. So there's more rainfall that they're capturing. So they have better information.
And also, will you be making any recommendations on zoning changes regarding hardscape to, when you have 50% hardscape?
I mean, that's not part of this project, but I think the city's committed to, making improvements to minimize, impervious areas and to maximize nature-based solutions. That's where everybody's headed because you need to get back to that model where you're using nature-based solutions. And the day of collecting impervious areas and routing it through the system are over. And they're over now, and they're going to be more than that in the future. So there'll be a commitment to utilize these green infrastructure, nature-based solutions, underground storage, and, as far as the policy goes, yes, probably getting to a point where, permeable pavers are going to be the recommendation when it comes to hardscapes. Yes.
Thank you, William and Kiara, for the wonderful presentation. My name is Hassan. I'm a graduate student at WPI. What we are looking alongside John's office is winter climate adaptation. What we've looked at is there's due to increased weather in the winter from December to February, there's increased precipitation, so more rain. That's what the data is telling us when we look at NOAA and the weather station here at the airport. We wanted to ask, is that something you're considering while you are analyzing the stormwater mechanism of the water runoff for both the present and especially in the future? Or are you just looking at the data set for the whole year and the rain?
Yeah, I mean, that's a.
Can you recap the question for us?
He's concerned about, if you notice the last few years, there's more rain in the winter than snow.
Mhm.
So how is that impacting the designs as opposed to rain that happens in the summertime? Okay, so the overall scheme of that is, rain that happens in the winter now becomes 100% impervious. All the areas that were pervious in the summertime are no longer pervious. So that's naturally going to be an increase in runoff. That's not a design storm that you look at because it's like max worst case scenario. And if you design based off of that, it would most likely be cost prohibitive. When you select a design storm, you have to pick a design storm that's going to best serve the population. And there's always going to be a storm that comes along higher than the design storm that the system will probably fail. But that winter situation is definitely something to be concerned about.
Where that would happen, there would be a chance of increased vulnerability in those areas. To just add into it, if that area is vulnerable in its own, as you pointed out, the vulnerability that you looked at, if it's on a lower lying, more impervious area, and there's more rain than usual, then it's going to be a more higher chance of flooding.
Yes.
Are maps showing the areas which are currently flooding, the predicted flooding areas for 2070 and the projects, the 6 areas that have been selected for immediate projects? Are maps showing that available to the public anywhere?
They will be available. I think they've been posted in the past, but until they're finalized, I think there's going to be a point where they will be shared online. And
Yeah, in time. So part of it is, once you select the ones, there's always going to be questions as to why the ones you didn't select and why. And so we got to walk through that and make it very clear so that it's pretty self-explanatory as to why we've chosen what we've chosen. And so that's the phase we're in now. So we're working on that.
Yeah, and that doesn't exclude the city from doing future work.
Absolutely.
That was, yeah, that's how many, and that's what was included in the budget essentially. So you have to pick a number and then plan for it. So,
It's the first six.
yeah.
And as far as other areas, again, this is a model that we're predicting something would happen under the existing conditions. If we have a neighborhood that floods in the model right now, but there's no documentation of it flooding in the real world based off city documentation and calls that they address, that's an area where we need to do further calibration of the model to fine tune it. And that'll be part of the next phases too. When it comes to publishing information, we would only publish information that was rock solid, backed up with field verification and, confirmation of, the model matching up with real world conditions. So there's a lot of areas that we have identified that potentially right now, the model says are problem areas, but they're going to need some fine tuning if it's not true. Okay. Yes.
And thanks. Do you run the models with the potential mitigation measures, both the green infrastructure and the gray infrastructure? And if so, what reduction of flooding can be expected with those measures taken?
Yes, they will be run together. We're in the process of doing the detailed analysis. So when it comes to the rain volumes, the 2070 number is very extensive. Okay, it's a large number. And when you look at the models and the impacts of gray infrastructure, we'll be looking at the 10-year, 24-hour rainfall, because that gives you the largest volume of water that you have to deal with. And when it comes to green infrastructure and nature-based designs, we do the 2-year, 6-hour, because it's a smaller storm event. Once you get into those high storm events, the green infrastructure basically are overtopping. Okay, so they'll be done separately on 2 different models and combined at the end to come up with the best product for that watershed. But know that they're 2 different storm events and 2 different design storms based off of what they can resolve.
Just one more question.
Just wondering, so there's the combined sewer area, and I know that's separate from this particular model, but what's the plan for integrating the results of this work into that? And what provisions have been included along the way in case that to plan for the future for trying to build on what you've done here?
Well, I guess the big concern is the combined area. We will work with the consultant and we will work with the city and make sure that these projects are in line. But what you're looking to do is make sure that you're going to separate something in the combined area so that sewer flows are now in the sewer, storm drains are now in the storm drains. Well, now that storm drain needs to go somewhere. Where is it going to go? So we would work with the other client about discharge points. If they want to discharge into sub area 7, where we know we have a lot of problems, we would have to include that tributary area so that we account for that flow. So there would be a lot of back and forth with all these projects, especially when it comes to separation. Because once you separate, that water now has to go somewhere. Is it going directly to an outfall that goes to Beaver Brook? Or is it going to a local drainage system and then goes to Beaver Brook? So there's a lot of the stuff that has to be worked out with those details.
Yeah, and it's my understanding that that project will be done next year, like finished.
Fingers crossed. Okay. I guess that's it.
Yeah, so thank you guys.